Here are the first 20 natural numbers. Among them, these are the primes. Just 8 in this range. But as we expand our view, we now count 30 primes in the first 115 numbers. In fact, there is prime counting function called pi of x that is counting the number of prime numbers less than or equal to some real number x. But we'll ignore this fact for the video purpose. Though primes grow rarer, they never disappear. Why? The answer lies in a 2,300-year-old proof. Euclid asked, "Are primes infinite?" To prove it, he used a clever trick. Assume the opposite and show it leads to a contradiction. Let's peek into his proof. Suppose only finitely many primes exist. Multiply them all to get a product, p capital. Now add 1 to p to create a new number, q. Divide q by p1. Remainder is 1. By the way, k1 is equal to product of all primes except p1.
So p1 isn't a factor of q.
Divide by p2. Again, remainder 1. k2 is equal to product of all primes except p2.
Thus, p2 also isn't a factor of q.
Using this logic, we can find that none of the prime factors of p capital divide q. This means q isn't divisible by any prime in our list. So q must either be a new prime itself or made of entirely new primes. Either way, our original list was incomplete, a contradiction. Thus, the assumption fails. Primes cannot be finite. Euclid's logic even gives a way to generate new primes endlessly. Let's test this. Take the primes 2, 3, and 5. Their product is 30. Adding 1 gives q equals 31. A new prime. Now the first 6 primes. Their product is 30,030. Here, q equals 30,031. Isn't prime. But its factors, 59 and 509, are new primes missing from our original list. The proof holds. Though primes thin out, Euclid proved they never end, a glimpse into the infinite.